So now the second speaker will talk about MiCOMP, and the second speaker is Amir Ashouri, who's coming now. This is work that was done, that's a joint work between the Politecnico di Milano and University of Delaware, where Amir was in a HiPEAC mobility program, so that's another proof of the utility of HiPEAC, we all know this. And Amir did his PhD at Politecnico di Milano and is now a postdoc fellow at the University of Toronto. So it's all yours.
Thank you. Can I
have this one? Yeah.
Okay. So welcome everyone. My name is Amir Ashouri. So the work I'm going to be presenting today is called MiCOMP. It's an acronym for the phrase we use for the title, mitigating the compiler phase ordering problem using optimization, subsequences, and machine learning. So this was the work initiated in my lateral stage of PhD, and yeah, as Oliver said, thank you. I'm also excited to deliver a project that was initiated by HiPEAC Mobility to a HiPEAC conference. All right, so this is going to be the high level of my presentation. So at first, I'm going to start by introduction of the problems, the major problems we have in compiler auto-tuning field, and then I'll start explaining MiCOMP methodology. So what MiCOMP brings is introducing subsequences. So we cluster sequences into subsequences, and we use subsequences in a machine learning-based model. So in order to use that, we propose an encoder and also a recommendation algorithm to speed up the exploration. And at the end, I'll have the experimental result and the conclusion. All right. So, I mean, this is a HiPEAC conference. This is the compilation track, so everyone is familiar with compiler optimization. So, for instance, we have many optimizations available in the modern compiler frameworks like LLVM, GCC, or Intel ICC. They have more than 100, or in some cases more than 200 optimizations available. And each of those, by using each of those, you can reach to certain goal. So the goal could be performance, reaching high performance. Or in the past, it used to be code size. Or at the same time, we are interested in controlling the power metrics. So what the compiler passes can bring us pose also a challenge. The challenge are classified in two major classes, which it was known in the field as the selection of the best compiler flags, or identifying the right compiler flags to choose, and also the phase ordering of those. So what if we play with the phases and apply repetition as well? And that's where compiler tuning comes into phase. So if you want to have a quick definition for tuning, it stands for automatic code generation and code optimization as well. At the same time, we are interested in optimizing certain objectives. So minimizing energy consumption and maximizing performance at the same time. So historically in the 90s, it was used in the backend, but the downsides of playing with the backend optimization is that every time you want to change something or you want to add something to your compiler, you have to open it up from the backend, and it requires exclusive knowledge of compiler engineer. And for sure, it has higher overhead to modify with respect to using the passes in the front end. So, as an example, so the work I'm presenting is tackling phase ordering problem, but in order to know the phase ordering problem, let's just have a look at what selection problem is. So the selection problem is when you have several compiler passes and you want to identify which one is more suitable for you, for your application, and this data set if you want to use it. So suppose you have n optimizations like loop unrolling, LICM, BCE, and you have O as the number of available optimization levels. So like loop unrolling has 3 levels, level 1, level 2, and level 3. So having that, you're going to have a binary space that is exponential. So suppose you have N5 and N3. So you can have a variation as loop unrolling, tiling, DC, loop fusion, or using 3 of those, having loop unrolling on its 3rd level and tiling on its 2 level, and so on and so forth. So you see, by having only 5 optimizations, we're going to have an optimization space of 72. So suppose if you just go to LVM world, to GCC world, you're going to have in order of millions and billions of optimization passes to choose. All right, in the past, in the late 90s, people were using iterative compilation. So the very first paper that introduced iterative compilation was by several guys in India and Professor O'Boyle. And so iterative compilation simply stands for iteratively compiling your code using different passes and capture the metrics they're going to bring you and simply choose the best version out of that. It's like somebody is tossing the coin for you, and at each toss of the coin you have a new vector of optimization, and then you test that optimization and you're going to have the output of that. So certainly it has advantages. At some point you're going to have a better performance because randomly you can go on forever and you can outperform the existing performance. But the downside is it's going to take forever, and there's no guarantee you can find a better better speed up. So can we do better in this process? Of course, if we add knowledge, or if we simply use machine learning or using heuristic-based models, it has shown that in the past 20 years we can outperform iterative compilation or be at least equally good, and we can transform and transfer the knowledge to other applications and data sets as well. Because iterative compilation at the end, it's going to be application dependent. So a new application comes, you have to start from scratch. All right, so I know we have so many papers in the field. I just wanted to put some that stands out. So starting from late 70s, you see it's a pretty old research topic that is still an open issue. So starting from late 70s and 80s and 90s, so people have been introducing learning methods and using, trying to tackle back-end optimization without machine learning. In the late 90s, Cooper started to use generative algorithm. There are other works in the early 2000s. And then iterative compilation started, late 90s. And 2006, Agakov and the other authors in Edinburgh mastered the work with the machine learning model. So this is an important paper in the field right now. And then later on, Cavazos and EJ Parker started to use other type of features instead of static features, so dynamic features as well. And we had phase ordering as of late as well. So just a quick point here. So we've been, the last year, we tried to analyze the whole field, the compiler optimization field, using machine learning, and we managed to gather a survey by analyzing more than 200 papers on that. So this is a snapshot of the survey. So it currently is under minor revision at the computing survey. So I'm planning to, I've already put a fork on that at archive, and I'm planning to update that quarterly. So if any papers comes out, if I wasn't notice of that, please send it to me. I'll be happy to add it. So we plan to have the concurrent version in archive so that it keeps updated. And so we have classified and clustered the research by using different compiler concepts, different characterization techniques, different machine learning models, and prediction time. All right, so that brings me to define the difference between having an intermediate speed-up prediction or full sequence prediction, which people have been using for tackling phase ordering in the machine learning domain. So let's just have a quick definition for phase ordering. So it was first introduced at the late 90s, so at late 70s, so 1979. And as you know, there is no ideal ordering of phases because, first of all, the optimization vector could go on and expand forever, so there is no bounded, and it's not deterministic. So the definition says there is no ideal ordering of phases. So suppose optimization pass A will transform the program in a way that optimization B could make it worse or obliterate the effect that could have been done otherwise. The optimization space is much, much larger than a selection problem. as you see, suppose you have 5 optimizations, and you want to down your optimization vector only to 5. Like you don't want to have it unbounded. So let's see what's going to happen. Also, consider the fact that in trace ordering, we can have repetition. Sometimes people are using loop unrolling twice, or you have some optimizations that you need to apply, like dead code elimination afterward, and then another optimization that you need to use dead code elimination after that as well. So repetition is happening. If you take a look at the standard optimization levels like O2-O3, they have many repetitions of the same optimization normally inside. So you want to have different variety of optimization vector using those 5, and simply adding them, you're going to see that by 5 optimization, you're going to have around 4,000 different combinations if you want to optimize the code. So suppose if you go to LLM board, it's going to be like order of billions and billions. I put a small example here. So the major issue that people could not tackle the phase ordering problem as much as we have many papers in the selection problem is that you simply by letting n is equal to 20, you see different order is enormous. So 10 to the raise of 7, and the other side you have at least 10 to the raise of 18, even without the repetition case. So you add repetition, it's going to be even more. So what we were thinking about was, can we first reduce the optimization space in a way that the performance we gain doesn't go worse. So that's why we thought about clustering methods. So in the past, we've been having papers that applied random clusterings or manual clustering using the compiler knowledge. So we thought we should expand this in a way that it's going to be automatic clustering. And as well, instead of going for a sequence predictor, which predicts the sequence for you, we went for a speed-up predictor. So a speed-up predictor is sort of a machine learning-based predictor that you pass as input the optimization vector, and it's going to predict you the speed-up of that vector, so without you having to run on your machine. So it's going to save you time if you want to have, if you want to run it for 1 million times. So it's going to save you 1 million times of execution and compilation. So that's what they call a speed-up predictor. So we based our methodology on a speed-up predictor, and then so what we've seen in a field was before we had a couple of papers applying intermediate speed-up predictor. So there was a subfield that predicts based on each state of the code the next best option to apply. So suppose your program has been already optimized and is in a transform. You've already applied loop unrolling. So you are in a transform version dash loop unrolling. So on that state, you need to have another continuous program characterization collection, and then your model comes and tell you at this point and this state use the next optimization like TCE. But if you want to go for a full sequence predictor, which we try to introduce by MiCOMP, when a program comes at one shot, it's going to tell you this is the program, and this vector of optimization is most suitable for you, and you can use it. So the superiority of this approach is going to reduce the number of times we have to characterize the application, because there is no state here. But at the same time, the downside is it's harder to build. You need to have an encoding scheme, because phase ordering lets you have a variable length. Like you can have a length of 3, you can have a length of 5 or 7, or you have repetition inside that length. So you have to be able to encode them and decode them back to understand which was the most promising compiler passes that the machine learning tool has been predicted to you. All right, as an example, so this is what an intermediate speed-up prediction works. So you've built your model and you want to use that prediction time. You have to have a stop condition. The stop condition could be the number of times you want to predict, or reaching certain speed up, like 1.5 or 2. Unless it hasn't, hit the stop condition, it's going to carry on. So your program comes on. So here, So here are the program features. I just changed the color here because it accepts. It could be on another state rather than the baseline. So it was already. So this program feature already changed by the previous optimization. So we want to predict for this the next best optimization to apply. So it's going to query your speed up prediction model, and then it will tell you at this point use pass A. So on the next run, because you haven't hit still the stop condition, it queries the model again, and at this point you see you have a change in your program features here. That's why I changed this. So suppose by applying A, this program feature has changed. So you characterize it, and then you have different program features. It's going to query the model, and then it will come back and say, at this point, apply B. And it's going to go forever. At this point, we might have repetition. So the predictor decides, okay, it might be needed to have another bit here. And as an example, we hit the stop condition, and then the final optimization would be for you A, B, and B. So this is how an intermediate speed up predictor works. So if we go for full sequence, the same program comes, but instead the program features are only at the baseline of the compilation. We don't need to have it per state. It's going to query the model, and at one shot, it's going to let you know that, for instance, for this program, you can use the optimizations A, B, B, and C. So certainly there is advantage in having a full sequence speed up predictor. However, there are challenges. So how did we tackle those challenges? So first, as I mentioned, we have an enormous problem optimization space. So MiCOMP had to use an automated clustering method to cluster 100 and something passes into only 5 and 6. Second one was, it was variable lengths. You had to make sure that it's going to come back to a fixed length variable. And then the space was huge, so we had to use a recommendation scheme. All right, so that was the methodology. We started by training, characterizing applications. We did the dimension reduction. And then on the other side, our clustering came here. We explored the space and then used the LLVM backend. We got the speed up predictions with respect to the O3, and then we put it back. And the encoder comes here to make sure there are no variable lengths here. So that was the first contribution that I mentioned was the clustering, and this one was the second contribution, the encoder. At the prediction time, when we want to predict for a new application, the test application comes, we redo the same process, characterize an application, dimension reduction, and then at this point, in order to speed up the process, we adopted the recommendation scheme to find better solutions for us and converge faster to optimal works. All right. So since the details are in a paper and I don't want to run out of time, I'm just going to go fast on these methods so you can refer to the paper anytime. So in a high level explanation, so we started by analyzing the optimization level O3, which has around 160 optimization passes. So we started to analyze the pair of passes that has been consecutively appearing on that optimization pass. And we generated an optimization dependency graph, and we count them by the number of times this pair has been on the same O3 optimization pass. So this will let us to generate a graph for optimization O3. So these are the 60 unique passes that are in LLVM O3, and you see the higher the number of consecutively pairing, the wider the length of the arrow. Like it shows that like DCE on it shows that DCE and int combined, like having 3 or 4 times pairing together. So this one was coming before that. And this will allow us to apply a clustering technique, which we use agglomerative clustering. The details are in the paper, so I'm not going to present it. It iteratively tries to cluster and add more clusters unless it satisfies the path integral condition of that. So at the end, we were able to cluster to 5 clusters, which we call subsequences. So you can see on the table, subsequence A, B, C, and D. And that's why instead of using all these flags, we only use subsequences of flags. So, and we call them A, B, C, D, and E. And this way, we are downsizing a lot the optimization space. At the same time, we preserve what it was meant to be preserved. Because O3 was built tentatively by compiler engineers, so at some point it makes sense that 2 pairs are coming in certain order. All right, as an encoder, I'm pretty sure all of you are familiar with one-hot encoder. So we wanted to have an encoder that preserved not only the position and the name of the subsequences, but also the repetition as well. So suppose we have now 2 repetitions of D. So when we predict using this encoding scheme, we should be able to retrieve it back, and we understand that okay, 00110 was meant to be D, and 1000 was meant to be A. So this is like encoding and decoding scheme, and it's one-to-one, so you can map and then retrieve it back. And this way we started to train our model. And you see, using this scheme, we always have the same length, so there's no problem in having a variable length here. All right. Also, to speed up the process, we use a recommendation system algorithm. It's been there for like 10 or 15 years. So recommendation is a method to, when you have predictions, how you want to traverse those predictions and recommend good choices. So these choices could be books, like what Amazon does, or in our case, it was compiler sequences. So we use adjusted cosine similarity, again, the details are in the paper, to speed up that process. And instead of using static features like just speed up, we were looking into dynamic information. So what dynamic information brought us was to traverse non-similar compiler sequences within our data set, so we could explore more our optimization space in a faster way. So we could converge to more optimal points sooner than the previous approach. So this is the method. So this will calculate the similarity between the compiler paths I and J in all our data set. So we have to have the speed up achieved by that specific compiler sequence when applied to program P by the average speed up on the whole data set of programs. All right. So let's just have the result. So before we have the experimental result, we have to set the compilation baseline. So at first we thought, okay, let's start, since we are using O3, let's have the compilation baseline to O3. But it turns out if we use a compilation baseline and also the same passes after that baseline, you're going to be bound, and we can't go higher than certain percentage because you've already used all those passes, literally. So we decided not to use any compilation baseline. So that's why this line stands for. So these are the different optimization sequences sorted by speed up, and this is the speed up, and this line stands for speed up with respect to O3. So you see MiCOMP subsequences start lower, obviously, because they don't have any baseline, but eventually you're going to pass O3 itself, and you're going to go way beyond that, around 1.3. And this was the region of interest for us. Because when you pair this model with a machine learning model and use that recommendation system, you can reach that faster. So in 2 or 3 steps, you can reach that region of interest and just avoid, getting saturated there easily. So that was our compilation baseline. And also, we had to decide what the maximum allowed compiler sequence length that we have to use. As you know, it's going to have a huge impact on our, training sets. So if you allow your length to be of 3, you have like 156 different optimizations. But if you just allow it to 7, it's going to be around 100K per applications and per data set. So it would be a huge, it would take for months to collect the data. And we noticed that, okay, by allowing that up to 6, we still have sort of equal upper bound while avoiding 100K exploration at the same time. So we fixed our maximum allowed sequence length up to 6. This accounts for around 20K per application to explore in this way. All right, so now we set everything. So the compiler flag, the compiler optimization, the compiler framework we used was the LLVM 3.8. No compilation, as I explained. The performance comparison still had to be done by O3. We used the benchmark suite of CTUnit, 32C applications. So the maximum allowed was 6. The application characterization has been done by a tool called MiCOMP. So, and the dimension reduction has been done by principal component analysis. Again, all these details are in the paper, so I'm just gonna showcase them for you here. So we set the principal component analysis to 5. We applied 3 machine learning algorithms because this method is machine learning independent, so you can pair with any machine learning you are interested. So we use 3 linear regression, K-star, and MLP, and the training and testing was done in leave one out cross-validation method. All right, so that was the prediction error rate, and you see by using our encoding scheme, we could, and we captured 2 different error rates, so it's called approximation error and mean absolute error, and these are our 3 different machine learning models. So you see MiCOMP encoding has a substantial benefit because it's going to reduce up to around 2x the error rate. So starting from 12 or 13%, we can come back around 5 to 6% error rate, which is an acceptable error rate when you use conventional machine learning tools. And also at the same time, when we use the recommendation scheme with the adjusted cosine similarity that I explained, we could outperform the state-of-the-art ranking approach, which was introduced by Cavazos, EJ Park. So they were to sort the predicted speedup by their speedup, and then they were to choose the top n as their solution. So their top 1 approach was the best number 1 on that list. So you see, our top 1 approach can outperform, and the scale up to top 20 approach, we always standing in a better position because we're using dynamic information, and we can go for other location in the space faster. We can switch. All right. So as an overhead, I just put the whole offline training and online prediction. So offline training was done only once, so you don't have to redo it. But online prediction, you just have to take into account the average compilation and the execution time. So if you exclude that, because anyways, if you did not want to use MiCOMP, you had to compile the list and run it once. So you have to deduct these 2 numbers from the rest of the 5, so it accounts for around 2 compilation and execution time. So if you use MiCOMP, that's kind of the overhead you have to pay, which is still acceptable because when you compare it with the standard optimization levels, you see that on average, on 2 or up to 3 steps, you can outperform O3 itself. And the second number, the B%, is the percentage of the space we explored by reaching that. So the space of us was around 20K. So by just exploring less than 1% of the space, we could find a good solution that could outperform O3. That was another comparison with the iterative, random iterative compilation. You see, our bars here, white bars, are located in a much higher, so we could outperform iterative compilation at each step as well. So, and then, and the final result is the other work of John Cavazos, which was having that intermittent speed of prediction. So these are the steps. I'm not sure if it's readable. So on 26 out of 32 applications of C-Bench, we could outperform the other work. And on average, we gained around 5%. So we were like, this is speed up and their approach, but at that point, so we could outperform by 5% around the other work. All right, this was another state-of-the-art comparisons which I'm not going to explain due to lack of time. So to wrap up, MiCOMP proposed the first full sequence prediction model for the compiler phase ordering problem. We proposed and presented an automated clustering technique. We proposed an encoder and also an exploration policy to speed up the process we had. The future works for sure. We're gonna have heterogeneous board. We have to use more GPUs. At the same time, we have to have fast and more accurate models. So deep learning comes handy. So there was some good papers recently, like in CGO this year. They'll be using LSTM deep learning model. So certainly that would be an option if you want to go forward from now on. And that leaves me just a 30-second quick positive note for my younger fellows. So you can see the chronology of MiCOMP here. So we started the research at late 2015 when I came back from University of Delaware. And so that's the timeline. And the first version I submitted to ACM LC test, and it came back, it got rejected. So like you see, we had weak accept, reject, and weak reject. So I said, okay, I got the review, and I resubmitted back to cases that year. So the result came back, we got demolished, like 4 rejects. I mean, the chances that you get 5 rejects out of 4 rejects out of 4 is like maybe 5%, considering you have 5 values, like the strong accept to reject. And then we got the reviews again. I submitted it to HiPEAC. At this point, the paper got long because we had to address many other things. So I said, okay, let's go for Taco. It allows me to have more space on that. We got rejected again. So we got a major revision, minor revision, and a reject. So the result came out reject. So it was at this point, September 2016. I got the reviews again. It was in my final letter of my PhD. And we submitted again to Taco. Finally, we got a major revision, and then carry on forward, the 5th edition, we got a minor revision, and then finally, it got accepted, so this year, June. So just don't get disappointed when you get rejected. That's no suicidal thought, because you can carry on, that's fine. And yeah, that will lead me to, I'll be happy to ask, get some questions. Thank you.
Thank you, Amir. Okay, questions indeed. Okay, so I have one.
Sure.
About the clustering of the various optimizations. If I understood correctly, you said that you were taking into account the ordering of several optimizations that they had done by people. Because you said this is likely to make sense because this ordering has been done by people who know what they are doing. Don't you think that by doing this, you might be wasting the opportunity to detecting new ordering that have been so far unforeseen and that could lead unexpectedly good results?
Yeah, I mean, this is absolutely possible. But the point is, when you have an optimization space of 1 billion or billions of billions, you have to start at least from one point or good enough point to play with those. I mean, we could start with completely randomized clustering using random generation of compile passes, but it would just take us longer to reach that region of interest that I mentioned. So yeah, so that's why we thought, starting from a good enough point, we are still be able to reorder O3, because when we subsequence O3 and use repetition on that, so when you use subsequence A, B, and then again A, you're literally reordering it, but it's like they're internally fixed, but they're externally reordered. Yeah, definitely, at some point, we might be bounded again, so we might be saturated at some point. But I think that way it will take us longer to reach a better point. Yeah, but for sure, it's possible, yeah.
Questions?
So I wasn't sure. I mean, maybe you could, say something about the. I think you called it the predictor. I mean, so can you say a little bit about that? I mean, how were you predicting, I guess, the expected performance? What features were you looking at? I assume it was, it was a static predictor. You weren't, a lot of the iterative techniques will actually run code and then, kind of look at the result there. So I'm curious about that predictor
I see.
and, how accurate.
Well, the accuracy of our prediction was around 5%, as was shown on that table. But our, feature characterization technique was brought from a tool called MiCOMP. So MiCOMP was a pin tool plugin. So it was dynamically instrumenting the code, and it is said to be, microarchitecture independent. So we've been testing it for quite a while. So I did test it on some, x86 machines, so I could use cross validation results. So and the performance was good. So if you're interested in that type, so the MiCOMP, the instructions that you can get out of MiCOMP is these 7 classes like I-types, PPM, register, stride, ILP, and so on.
So let me then, okay, that's helpful. Let me ask this. So I'm a user of your MiCOMP, and I've got a program and I want to use it. How long is it going to take me to compile my program?
I see. Let me just go back to that overhead. So if I can find that table of overhead, you can see at worst you have to compile and run your application once, because you have to fetch the program features. And then it's going to take some seconds that recommendation algorithm work, and some seconds that the prediction works. So the overhead, as we estimated, was around 2 times the compilation and execution time. So you're spending 2 times execution time, but then you're going to have the results right away. And the recommendation algorithm makes sure that you have the best results faster. So it's going to predict you the most likelihood one, and then it's going to show you, use this path for that application.
So, like concrete terms, I have a big program that takes 30 minutes to compile. Are you saying now it only takes an hour? Or
yeah. Okay. But given the fact that you already have the training set, because training set, yeah, that's right.
Okay, thanks. We'll have to stop here. Thanks again, Amir.
Thank you.